about, yeah,
The
Lorenzo.
question about the new problem you gave us, the bottom,
Uh-huh.
is it supposed to be UTS, yield strength?
Oh, my goodness.
Modulus?
Yeah. Thanks for catching that, Lorenzo. Any questions? Okay, so I introduced crystal defects, and then we talked about vacancies. What do I have? So this handy. But I think next week is the first exam, a week from today. I don't have,
Yes, it is.
yeah, is it? Okay. And I believe that today's lecture is the last lecture on that. If you look at that syllabus again, it'll say what topics are on the, so exam 1 is topics 1 through 15. So that's through today's lecture. Okay. So we're talking about what are called solid solutions. Solid solution, well, obviously it's solid, which kind of is different than our mental image of what a solution is. There's a solvent and a solute, and they're both solid. The solute is just the thing that there's less of. Okay? And together they form a solution. And in order for one metal to be able to dissolve or make itself into a single phase with another metal, certain things have to be true. The most important thing is they have to have the same crystal structure. So if I want to dissolve, well, let's see, from your homework, there's a nice table here. So nickel is FCC, and it doesn't dissolve in room temperature iron, manganese, chromium, or tungsten, because they've got different crystal structures. So solubility, or the ability of one solid to dissolve in another, and usually this is by what we call diffusion. Atoms of the one solid diffuse into the crystal structure of the other. So these are called the solubility rules. What might be another reason why one metal, the atoms of one metal, could fit or not fit into the crystal structure of another metal? Basically, these atoms diffuse into the vacancies. We talk about vacancies. They just take their place there. So what might prohibit that from happening? What might keep that from happening, Lorenzo?
There are no vacancies.
Well, sure, if there are no vacancies, absolutely, but let's assume that there are vacancies. What has to be true about the solute atom that allows it to dissolve into the solvent atom, solvent crystal structure? There's only so much room. So the atomic radii have to be reasonably similar. So if you look at that, at your homework again, homework number 2, that table in the bottom, nickel has atomic radii of 124 picometers. Platinum has a atomic radius of 139, and lead has an atomic radius of 175. There's a bit of a range there. The general rule of thumb is that at a minimum, the difference can't be more than 15%. And the extent to which they're soluble is very much a function of that difference. So the 15% increase in radius from nickel, 124, that would be 18 more, 142. So anything with an atomic radius bigger than 142, that would be aluminum, silver, gold, and lead, wouldn't dissolve well in nickel, or vice versa. Okay? That does seem like a double negative. How about this? So, silver and gold have the same exact atomic radius. So they're almost 100% soluble in one another. The closer the radii, the more soluble. And the last thing, which isn't always true, but it's usually, they should have the similar atomic valence. So at the end of that table, almost at the end, are the valences. If you look all the way down, silver and gold, gold can have a valence of 3 and 1, silver only 1, but they do share that valence of 1, so that allows them to be soluble. So, look at tin and tell me what metals are soluble in tin based on those 3 rules. Well, the first thing you're going to do is eliminate everything that's not FCC. Atomic weight doesn't matter. properties don't matter, density doesn't matter, but radius does. And 15% bigger than 140 would be 161. Down to 139. Okay, so somebody give me a metal that's soluble in tin. Michael? Platinum. Let's see, platinum, same crystal structure, fits as far as radius, also has a valence of 2 or 4, okay. Anything else? Jacob?
Molybdenum.
Aluminum, did you say?
Molybdenum.
Molybdenum. Yeah, I left that crystal structure blank because it was in your homework. What did that end up being in the crystal structure for your homework? Is it FCC or BCC?
XCC.
Okay, so that's good, radius is good, and they both have 2, good. Another? Soluble in tin.
Wait, how did the valence electrons match on that one?
What's that?
Is tin as a outer of 4 or is that inner of 4?
What are you saying?
The
That means either 2 or 4, either is, works. So, lead's too big, gotta knock that one out. Silver and gold don't have valence matching, nor does aluminum. We got platinum, got molybdenum. What about copper? Isn't tin copper, that's is it brass? No, that's zinc copper. Tin copper, it's not bronze, but I think it's something that is used at least in art. How about nickel? 24, that works, yeah, nickel would be as well.
how are you matching the valences?
So it doesn't have to have all the same valences,
Okay.
right? But it has to share a valence,
Only one.
only one,
So if it has a 2 or a 4,
yep, it
the
works,
other one is a 2 or a 4.
yep.
Okay.
Lorenzo?
So the radii can be smaller,
Mm-hmm.
but not 15% bigger.
Right. The difference shouldn't be more than 15%.
But it could be,
It could be
It's
15% smaller or 15% bigger.
but it can't
Up
be.
to, I'm sorry, up to
it can't be
15%.
Smaller than 15%?
It can be up to 15% smaller,
Okay, got it.
yeah.
So there's a 30%,
Up to and smaller, it seems like,
30% window.
correct, correct. And lead is like one of those that's, just so large that it's oftentimes not solid.
15% smaller is 180.
Okay. All right, so if I gave you on the test, or actually there might have been a question. No, but on a test, if I gave you a table like that, and I just asked you, gave you one of the metals and said which of the metals are soluble, you'd be able to do that. Right? Okay. All right. So how does the solute metal make its way into the solvent metal? You can't put them in a jar and stir them. The process is diffusion, right? Diffusion is the movement of one material into another. And so, let's see. There are a couple of equations that define diffusion. If I put two metals up against one another, two different metals, and I polished them so there's no oxide on their surface, and I put them right up next to one another, probably put them in an elevated temperature. The concentration, let's do the concentration of the blue in the red, okay? So I'm gonna plot that. So this will be concentration of the blue, whatever the blue metal is, versus depth. So at time equals 0, the concentration of blue is like, whatever that maximum is, it goes right to 0. Over time, the concentration gradient changes, and at some point, it's linear. So the slope of this would be the change in concentration divided by the change in depth. So what might be units of concentration? What might be a good unit for concentration, or units? If I'm looking for the concentration of something in a solution. Like, let's say I want to know the concentration of sugar in my tea. How might I express that? Diana?
Ratio.
I forgot my hearing aids today, sorry.
Ratio.
A ratio? Ratio of what?
How much of sugar compared to water? So like you can-
Right, so maybe like grams of sugar per unit volume of water, right? Concentration could be grams per cubic meter. Okay. So let's say that's grams per meter cubed. And depth, we'll just use meters, right? And notice that the concentration gradient, change in concentration, change in concentration with depth is negative. Concentration gradient is always negative. Things always move from high to low concentration. Okay, so let's say I want a measure of diffusion might be it might be something like the number of atoms that cross this area per unit time. Or maybe the mass, since we've got grams. So let's call flux the number of grams that cross a square meter per unit time. That's a diffusion flux. So diffusion or diffusivity is going to be some proportionality constant between this concentration gradient and the flux. And so the equation that we have is flux is J is equal to negative D times dC dx. So there's my concentration gradient. And there's my flux. So let's see, I've got grams per meter squared second on the left side of the equation equals something times grams per meter to the fourth. That's the concentration gradient units. So the units of D, kind of bizarre, would be meters squared per second. So diffusivity, the likelihood, speed at which one metal can diffuse into the other is as units of meters squared per second. It's kind of a weird unit, but that's where that comes from. Why do I have a negative sign on the right side of the equation? Jacob?
Because it's leaving the blue block.
Because why?
Is that because the grams are leaving the one block?
Well, yeah, or because dc dx is negative. Concentration gradient, which is kind of what you said. Because the concentration gradient is negative, if I just want to kind of make my sides of the equation balance, then I have to put a negative sign in that equation. Okay? And this is called Fick's first law. Fick was the guy who decided what the laws were going to be as far as diffusion. So, and this assumes steady state. It assumes that this is linear, that the atoms aren't accumulating or depleting, they're just moving through. Which isn't actually very typical. And in our purposes, for our purposes, when we talk about one element diffusing into a metal, it's usually at the surface because we're trying to harden the surface. And at the surface, it's typically not linear. And we'll get into the non-steady state equation in a moment. But that's Fick's first law. I don't usually give questions, like certainly on a test, maybe on homework, but I certainly don't, I usually don't write questions for the first law because it's like, well, it'd be like, the diffusion flux no, let's make it be the diffusivity of metal A into metal B at 250 degrees C is 2 times 10 to the negative 18 meters squared per second. If the concentration gradient is negative concentration change just multiply D times concentration gradient. B meter squared per second times -3 grams per meter cubed, meter fourth. We're gonna make that negative. It's that simple. A linear equation, there's not much to it. It's really basic, so I don't usually include questions like that. Because there's 3 unknowns, and you're given 2 of them. All right? Now, one thing I want to point out, though, is that diffusivity changes with temperature. So let's think about that. Why would the rate at which an atom moves into a solvent change with temperature? What would cause that to change? Yes, sir.
Because if you get an atom out, that atom starts moving faster.
Right. I mean, all the atoms are moving faster, so the chances of it moving by accident into the whatever we're diffusing into increases. There's another reason, and that has to do with vacancies. So let's take a step back and talk about impurities. We have substitutional impurities. And substitutional impurities are the impurities that take place of the solvent. A solute atom actually occupies the space of the solvent in the solvent crystal structure. And we've just written our rules for how that can happen. See solubility rules. So how does that happen? How does that move in? For substitutional impurities to diffuse into the solvent lattice, a vacancy has to be next to the solvent. So all these atoms are moving around. and all the vacancies are moving around. And I've got my impurity atom waiting for an opportunity to diffuse in. And that can only happen when a vacancy comes available for it to jump into. So, as temperature increases, atoms and vacancies move faster. Like, was it Jacob that said that? Who told me, who said they move faster? Ah, thank you. Some. What about the number of vacancies? How does that change with temperature? We talked about, we had an equation for that last time. And it caused thermal expansion.
It also increases the amount of vacancies.
The number of vacancies increases with temperature. So those two things together make diffusion faster with temperature. Now there's another kind of impurity. You've got substitutional impurities. We also have interstitial impurities. Interstitial, meaning in between. Interstitial impurities just fit in the tiny spaces between the metal atoms. So if we look at the face of an FCC metal, for example, there's one place that an interstitial atom could go. They don't need a vacancy. They can just move in between the atoms. How does temperature affect that? Well, this is still true. And the atoms are moving further, they're not moving faster, the atoms are moving bigger amounts, and so there may be more chance that the interstitial atom can fit through and get to the next open space. Diffusivity increases with temperature for interstitial impurities, but in general, diffusivity is faster for the impurities because they don't have to wait for a vacancy. Now, there aren't very many elements that are small enough to fit in between the spaces of metal atoms. Interstitial impurities are carbon, oxygen, hydrogen. Maybe nitrogen, maybe. But those three for sure. For most metals, hydrogen and oxygen are bad if they've diffused into the metal. They cause it to become brittle. Carbon is good. Carbon makes the metal stronger. So carbon, this is how carbon finds its place among iron atoms in steel. Okay, so temperature increases cause an increase in diffusivity. So what's that relationship? That looks a lot like the vacancy equation. This form of equation is called, you don't have to remember this, but you might hear it again, the Arrhenius form. Arrhenius equations are really common if you're in chemistry. So for this, this is diffusivity. At temperature T, that's in Kelvin. Diffusivity, meter squared per second. D0 is a diffusivity constant. And Q is the activation energy for diffusion. The diffusivity constant has meters squared per second, just like diffusion. The activation energy is joules per mole and these two constants are for a given set of solute solvent. So, here. These are constant. For a given solute, solvent pair. So the value of QV and D0 is unique for nickel diffusing in, what did we say? Nickel, copper? Nickel, copper, yeah. So nickel in copper has a unique QV or Q and D0. Copper in nickel has a different Q and D0. So the kinds of versions of this kind of a question might be, the simplest version would be given Q, D0, and T, calculate D. And I should have said, this R is the gas constant. Which is 8.31 joules per mole Kelvin. So the easiest version of a question would be, here's Q and D0 and the temperature, calculate diffusivity. A little bit more difficult or challenging version is given D1 at T1 and D2 at T2, calculate Q and D0. I guess I should also say for here, you could have given Q, D0, and D, find temperature T. Essentially, it's just, there's just one unknown. Whereas problem number 2 has 2 unknowns. Okay, so let's take a 10-minute break. I'm going to look up some values for D0 and Q, some metals, and we'll do some example questions. Most basic for copper diffusing into aluminum. Q is equal to those are the two type 1 questions. Let's do those first. The equation we've got is B equal D0 E minus Q over RT. And while we're here, let's also note that we could also use the equation natural log of D is equal to natural log of D0 minus Q over RT. All right, so for the first question, we could just write the equation in the simplest form. And we could say B is equal to D0, 6.5 times 10 to the negative 5. Let's go ahead and put those units. And then E to the minus Q, 136. And make sure if Q is given in kilojoules, that you give it in joules. 136,000 joules per mole divided by R, 8.31 joules per mole Kelvin times temperature, 500 C, 773 K. And I would say that the biggest thing to do is not just to let somebody else solve the problem and look on, because different calculators do exponents differently. So make sure you know how to do that on your calculator. Samu and Olivia get the prize. Now, Jacob, doing it yourself. So this exponent is negative 21.2. And e to the negative 21.2 you should get 6.21 times 10 negative 10. So we have that's equal to 4.04 times 10 to the negative 14. Anybody get that value? Yep. Anybody get that number? Yep? Cool, thank you. The second one, my unknown is T. So it's much easier, since my unknown is in the exponent, for me to solve this problem with that second equation. So here, I would say natural log of D, 1.2 times 10 to the negative 14 is equal to natural log of D0, 1.1 times 10 to the negative 4, minus Q, 272,000 joule per mole over 8.31 joules per mole Kelvin times T. T in Kelvin is 272,000 divided by 8.31 times 23. That's 1423 Kelvin, and I want it in degrees C, so I can subtract 273, and that's 1150 degrees C. Any questions on that? So these are examples of solving for one unknown when all the other unknowns are given. So there's only a single unknown. If you're given two temperatures and two diffusivities, and you're asked to find D0 and Q, and sometimes a diffusivity at another temperature. So let's see. Well, I can write it down. So this is type 2. And we'll do two problems here as well. So for carbon diffusing into nickel. At 600 C, D is 5.5 times 10 to the negative 14 meters squared per second. And at 700 C, D is equal to 3.9 times 10 to the negative 13. Find D0, Q, and D at 650 degrees C. So from algebra, if I have two unknowns, what do I need to solve for those two unknowns?
Two equations.
Two equations. And I do have, as it might not seem like it, but I do have two equations. I have one equation that says, let's see, I'll use the log form. Natural log of D, 5.5 times 10 to the negative 14 equals natural log of D0 minus Q over 8.31 times 873 Kelvin. And natural log of 3.9 times 10 to the negative 13 is equal to the natural log of D0 minus Q over 8.31 times 973. Equations. Two unknowns, D0 and Q. So, I'm going to have the first equation minus the second equation. All right, so natural log of the 5.5. tell me if there's anything there that doesn't make sense. Jacob?
How do you know that the natural log of D0 is going to be 0?
It's not, but I have this equation minus this equation. So I have natural log of D0 minus natural log of D0.
Thank you.
Mhm. You have to keep real close tabs on your negative signs. So once we know the value for Q, we can choose either equation and substitute Q in to solve for D0. So Tell me, which of these two numbers is bigger? Jacob?
The one at 700 degrees.
Right. A smaller negative exponent is a bigger number, right? A higher temperature is a bigger diffusivity, right? Now, we might be tempted, if we didn't know that this was an exponential function, if we were asked for the diffusivity of 750, just to find the midway point between the two. But that's not correct, because this is an exponential deal, so at 750, which is 1023 Kelvin, right? And B is D naught, 2.3 times 10 to the negative 6, e to the minus q. 1, 2, 6, 6, 6, 7 over 8.31 times 0.023. Oh, shoot. Did I want it at 750 or did I want it at 650? I did want it at 650. We solved it for 750. Oh. I guess we probably should fix that. I should get a number that's in between the two. I wasn't, when I do 750, it wasn't, but now it is. But it's closer to one temperature than the other, right? It's not a linear relationship. Okay, so let's do one more of those.
For an exam, how do you want us to round our numbers in between each equation?
So, when you're dealing with exponents, carrying the numbers is helpful, but in reality, it's not meaningful. So if you had just used 127 here, it would be okay.
Okay, because I calculated that and I got 1225.
Here?
Yeah. You guys calculated it wrong? I just
So
wanted,
did you have these same numbers?
for Q, I got goes there, I use 1.96
1.96?
over 0.16 10 to the negative 4.
Oh, and I was, yeah, all the way up here I'm using, yeah. So, Tim's point is that you get very different numbers at the end depending on how many significant digits you carry. And this is one of the areas of significant digits that makes us most uncomfortable because it seems like we're getting a very different answer. But remember that our numbers are, negative to the negative 13 power. So the magnitude of the difference seems bigger, but it's such a small number because it's such a small number, right? So I will want to look at your method, right? And that's what really matters. And your number might be very different from my number using significant digits. Okay, so some people think we're done, but we're not done. Want to do one more like this. And this is for nickel and iron. Now, nickel, FCC, iron, room temperature, BCC. Nickel won't diffuse into iron at room temperature. But you get iron to above 912C, and it's FCC. So, when you see these two different crystal structures, and you think, wait a minute, that can't happen. This is happening at 1473 and 1673 C. Okay. I'm sure it's C. Although it's kind of strange numbers. I bet it's C. Okay, let's do it this way. How did I write it before? For fusing nickel into iron at 1200 C. D is 2.2 times 10 to the negative 15. And at 1400 D is 4.8 times 10 to the negative 14. Find D0 and Q. Alright, so element of 2.2 times 10 to the 15. So element of 8 times 10 to the negative 14 is so negative 33.8 is equal to D0 minus Q over 8.31 times 1473. And negative 30.7 equals D0 minus Q So once you solve for D0, you're finished. Let's think about what's on the exam. would be like problems we worked in class or homework. And the form of those kinds of problems on an exam are just like they are on homework or in the notes. Fusion. Which is the phenomenon, I guess, of carburization and carburize